All right, good. I'm glad it's helping. I mean, I figured it was mostly for the people who, I just got back to review. Oh, okay, yeah. Yeah, if there's something that you couldn't remember, or yeah. I mean, it's mostly for the people, obviously, who can't make it for some reason. At least they can see what we're doing. But good, I'm glad you guys are using it too. Okay, so let's see how far we got. Let me scroll this down here. We got to, let me just put it up here. All right. Actually, I'll tell you what. Let me first take questions first, and then we will finish up the chapter. I think there's just one more reaction I think we have to talk about. But any questions, either Chapter 9 or Chapter 8 or homework stuff, especially homework based on stuff that we've talked about so far. If you guys want to go on the mic, it might be easier. If you have any questions, do that first. All right, no questions. You guys are good? Okay, Andrew has a question. I'll wait for you to type it in. On 6A on Chapter 9, let's see, 6A Chapter 9, use Mark's rule as first step. Can you also use anti-mark? Usually, I mean, just without looking at the question, you usually don't do anti-marks in this chapter. Anti-mark was just for alcohols, but let me see the exact question you're talking about. Yeah, the anti-mark is only that BH3, H2O2, and hydroxide that we learned about in Chapter 4. So you don't really go anti-mark in any other reaction. But let me just double check. So 6A. How would you carry out the following transformations? More than one step may be required. So you're going from hex 3-ene to hex 3-one. So let's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. You have a double bond right here. Oh, so in this case, there is no anti-mark. The reason is because you get the same product no matter which of these carbons you actually turn into a ketone. They are equivalent. So carry out, more than one step might be needed. So it just all depends on which route you go. So if you go the route, so you've learned that mercury one, like the mercury sulfate. So this is Chapter 4. I imagine they want you to try to do it as a chapter. Oh, wait a minute. Chapter 9. So if you get a ketone, so let's just call this carbon 3 and call this carbon 4. So if you get a carbonyl on carbon 3, it looks like this, right? So your carbonyl is on 1, 2, 3. If you get the carbonyl on carbon 4, right, 1, 2, 3, 4, but really I'd count it this way, 1, 2, 3. So these molecules are the same molecule. So there is no Merkovnikov or anti-Merkovnikov. They are equivalent spots. So no matter where you go, you get it. Oh, I think I got your question. Can you use anti-marks? Yes, you could, but you'll get the same product. So I think how you're doing it, so it would be either H3O plus in order to get the alcohol. Now in this case it's equal, so I would get a mixture of this compound plus the other mixture of this compound, but these are the same compound, and then oxidize it like PCC. But if you wanted to, you could also do the BH3 and the H2O2 and sodium hydroxide. Guess what? You'd get the same two compounds because there is no least substituted, it's equal. So if you're just saying, can I do this reaction instead of this one, the answer is yes. Yes, you can. But either way, it's the same thing. Okay, cool. Yep, that's a good question, Andrea. But usually you save anti-marks for if you just have to make a least substitute alcohol. If you just have to make an alcohol and then eventually oxidize it, if it's not a least substituted, then you can just use acid and water. You don't have to do anti-marks. But if you did, it's fine. Good. All right. Yep, that's a good question. All right, good. Any other questions? Let me, I meant to pull the book up so that we can just refer back to it. Let me find what my book is. All right, good. Anything else? Otherwise, we'll go ahead. Let's move all this stuff out of the way. All right. So let's finish up this chapter. We'll do some problems. Let's see. So we talked about Grignards a lot yesterday. That's kind of the big reaction. Just to review stuff. And then we talked about the hemiacetal and acetal. Any questions on that? That sometimes can be a little confusing. So, but usually when I go over the sugar stuff, people start seeing it because they kind of see how it can be important. And then what we talked about this stuff, like the cellulose and starch, hopefully you guys found that interesting and more relatable. We talked about the imines. We didn't really talk too much about it. Just basically, if you want to make an imine, you just use a ketone and a primary amine. Remember, this has got to be a primary amine because of the fact that this has got to be primary, which basically means you have to have these two hydrogens here because the oxygen and the two hydrogens form a molecule of water. If you do not have a primary, you cannot form an imine. All right. This is just the intermediate. What kind of happens? Did they show the mechanism? I'll tell you what. I'll go over the mechanism. It's I think it's helpful to actually look at it. Okay. So we have a carbonyl. What color do you guys want today? Let's do a different color. The whole rainbow. I think yellow is too bright. Let's do green. Green was. Let's do like a darker green. There we go. Okay. And then you have your amine. All right. Now this is usually done in acid. The reason I'm going over the mechanism is because you'll see that this mechanism is very similar to the mechanism of the hemiacetal and the acetal, and those mechanisms you need to know. I don't remember. Do I go over this mechanism in the videos? You guys can say yes or no in the comment. I don't remember if I go over this in the video. The imine formation. I thought you did. Yeah, I thought I did too. I'll go over it again. Yeah, so Lucas said yeah. I'll go over it again. That's fine. So since I did go over it, let's go over it. All right, so for all these, the first step is always protonation. The reason is because the carbonyl itself, even though this carbon right here is partial positive, right? The carbon right here is partial because the oxygen is partial negative. Nucleophiles can't just attack it on its own. It has to have a reason. So by protonating your oxygen, you're putting that positive charge on the oxygen. Well, oxygen does not want a positive charge. All right? So an oxygen is more electronegative than this carbon. So therefore, this oxygen is going to be pulling on these pi electrons. So these pi electrons are kind of wanting to go on the oxygen to stabilize this plus charge and put more of a plus charge on your carbon. So by doing this, it makes this carbon much more electrophilic now, so that your nitrogen can now finally attack into there. If I don't have the hydrogen, this cannot attack. It has no reason for it to attack. All right, but once you protonate and put a positive on the oxygen, now that oxygen really wants those electrons from the pi bond so that your nitrogen can finally attack into it and kick these electrons up. So that's kind of the driving force. Anytime you do these reactions, you usually have an equivalent of acid in there as a catalyst. All right? And in every case, what you're going to notice is you're always going to form a molecule of water. This oxygen that was part of the carbonyl, all right, usually it becomes water because you have to proton transfer. This oxygen is going to grab this proton. We saw the same exact step yesterday when we talked about the acetal and hemiacetal. These steps are identical, except in this case I have a nitrogen instead of an oxygen. Instead of two oxygens, I have an oxygen and a nitrogen. All right, so if you look at this intermediate, I know it looks a little different, but that intermediate looks very similar to this one that we have here, except I have the extra hydrogen on this OH. But notice I have a nitrogen with a hydrogen and R group attached to a carbon with an OH. In this case, same thing, nitrogen with a hydrogen R group, but rather than the OH, I have the water, because they really aren't showing like that mechanism very well, but there technically should be an equivalent of a H plus hanging off of that oxygen over there. All right, and then the driving force here, the water wants to leave. Again, oxygen does not want to have a plus charge. It wants these electrons, all right, to go to the oxygen. So in order for that to happen, these lone pairs on the nitrogen pop down to form your pi bond, which is what we want eventually, and kicks out that water molecule. So I know it's currently upside down, but it doesn't matter which direction we want. So R, and we still have this hydrogen hanging off of it with a plus charge. So, and the water left. And then water comes by and plucks off this hydrogen. And what are we reforming by doing that? You guys want to just mention? Yeah, our acid. Yes, we're reforming our catalyst, exactly. So in all these cases, the very last step is always this water plucks off a hydrogen to form and kind of spit out H3O+, which remember is the same thing as H+. So it's our catalyst. If we use our catalyst, we have to regenerate it somewhere, and this is the regeneration of the catalyst. Yep, good. Okay. All right. So that's imine formation. And we'll talk more about imines in chapter, let's see, when we get to the amine chapter, chapter 12, there's a good chance we might not get to it. We'll see. We're actually, things are going on schedule. I'm actually pleasantly, I'm not surprised. I knew I'd get back on schedule, especially since we have all the videos up. You know, if we don't have to push it, I'm not going to push it. I'm not going to push anything for the remainder of the semester. All right, let me put this back on. There we go. Okay. All right, so the last reaction, let me just double check my notes, make sure. Sometimes I'll add something in my notes that's not on the slides that I want to talk about. That usually is helpful in class. But I think Cornier's, conjugate addition. That's it. Okay, good. Yeah, this is the last thing. Okay, so this is what's called a conjugate addition. I'm going to talk about two different things that aren't really on here, or another thing that isn't on here. It just gives more information. So this is what's called a 1,4 addition. There's also something called a 1,2 addition. And believe it or not, up until now, this is what we have been all talking about. Even though you didn't realize it, we have been talking about a 1,2 addition. So let me just show you real quickly the difference between a 1,2 and a 1,4. All right, so a 1,2 versus a 1,4 addition. All right, so let's put, so a 1,2, well, yeah, a 1,2 addition is where your nucleophile, so the way that these numberings are coming in is that number 1 is your oxygen. That's number 1. Number 2 is the carbon attached to the oxygen. Carbon 3 is the first carbon on the double bond, and carbon 4 is the last carbon on the double bond. So 1, 2, 3, 4. A 1,2 addition is where your nucleophile attacks at the 2 position and kicks up the pi bond. So in this case, your product would be O minus plus you would have a nucleophile right there. So the Grignard reaction, we've seen that we have, if you have a carbonyl plus a Grignard, let's say a CH3 minus, right? It always attacks at the carbon. It kicks up the pi bond. It doesn't even matter if I have a double bond there, the 3,4 double bond, because it won't even attack there anyways. CH3. So a Grignard is a type of 1,2. Adding LAH is an example of a 1,2, where the hydride will attack right there. Okay, these are examples of 1,2 additions. Usually the 1,2 is strong nucleophiles. So something that has a negative charge, like a Grignard or a hydride of some sort. So that's what's considered as a 1,2 addition. So those are things that we have been doing up until now. Attacks the carbonyl. And the last example on the imine, it was adding onto our carbonyl carbon. A 1,4 addition is exactly how it sounds. It adds to the 4th carbon instead. Instead of acting to the carbon on the carbonyl, it adds to the carbon on the double bond. So I am going to delete this so that I can draw those out. Is everybody okay? Does everybody have this? Say no if you want me to keep it. Okay. So a 1,4 addition. So what this compound is it's an alpha beta unsaturated carbonyl. We talked about the alpha beta yesterday. In this case, it's a ketone. It could be an aldehyde. But alpha beta, remember the alpha carbon is the carbon next door to the carbonyl, and the beta carbon is the one right there. So this is called, and again, it's unsaturated because it's not saturated. So in this case, your nucleophile is going to attack this carbon instead. And what it does is it kicks up these pi electrons here and kicks up these into there. It's kind of like a domino effect. Or the magical R word. What's the magical R word? Resonance. Good. I'm glad I didn't start with F. So I'd say, what's the magical F word? Resonance. It's resonance. All right. Sorry, just getting a little punchy. All right, so there you go. So that's kind of the intermediate. And then what eventually happens, all right, is this electrons pop down, and then these will grab a hydrogen from somewhere. And I'll show you where. It's usually attached onto our nucleophile. So let's actually do that. This will grab the hydrogen off of our nucleophile, and you eventually form that compound. Okay, so you can either form this type of a compound, which is a 1,2. Let's put an H here because it usually turns into an alcohol. That's the 1,2 addition. The 1,4 addition, again, it's the same thing except you reform your carbonyl, and you just get it added onto there. 1,4. Okay. 1,2, strong nucleophiles. 1,4, weak nucleophiles. And usually they're alcohols or amines. Those are the common ones. There are other ones, but I think most of the cases you'll see in the book is either you're taking an alcohol or an amine and you're adding it onto there. Okay, so I want to show you a real example with a mechanism drawn out so you guys understand it. But any questions on this before I erase it? Alright, so let's take this compound and let's add methanol. I'm going to do it in a different color too, just so that it's good to see all the different colors. It's easy enough to change. Okay, so what's going to happen first is the lone pairs on your oxygen are going to add to this carbon, kick up these pi electrons, and then kick up those pi electrons. So the compound is going to look like sorry, I forgot a pi bond in there. Got a pi bond in here. Should pi bond right there. This is resonance. Okay. So the oxygen attacks the carbon, the pi bonds pop up and kick this up to give you the O negative. Now in this case, remember, you reform that pi bond. Right? You reform the pi bond. So what happens is this hydrogen right here, this red hydrogen, is going to get placed right here on this carbon, on the alpha carbon. All right, so let's see what happens. These electrons pop back down to reform your pi bond. Right here. All right, and then these electrons pop out to protonate this carbon right here. And then these electrons go onto your positively charged oxygen. So your final compound you have the H here, and you have your OCH3 right there. Now you don't have to write that hydrogen right here. I'm just writing it just to show you where it goes. But if you just want to write your final compound like this, it's totally fine. Okay, so it's basically the way that you can look at it is this oxygen gets hooked there, and this hydrogen gets hooked there. That's basically the overall reaction. Okay? Any questions on that? They just kind of show you more. So again, you have your alpha, beta, unsaturated ketones. It's just going to show you what the book does. Again, they give you more information, but they can kind of they show you. Let's get my pen here. All right, they're just showing you the resonance structures. See how they're showing you the resonant, how the pi bond goes up here to give you a plus charge, and these pi electrons go there to give you that. So they're just kind of, they don't really. So here's the reaction. Nucleophile adds to the beta carbon. Oh, they even have it alpha beta. That's good. I didn't realize that they do that for you guys. So that's good. And it gives you the intermediate. Now, remember I was saying it's actually a weak nucleophile. I know they have a negative here, but it's usually a weak nucleophile where there'll be a hydrogen attached to it. So you'll have a hydrogen hanging off of it. And then when these pop back down, this will grab the hydrogen. Because the negative charge, as you can see, is actually on that carbon right there. So that's why the hydrogen is protonated there. And then you have your nucleophile. So again, if you count this, 1, 2, 3, 4. So 1, 4. Don't worry about this word enolate. That's an enolate is just this compound where you have a negative charge carbon on the alpha carbon next door to a carbonyl. This negative charge is relatively stabilized. It's stabilized because it can form a resonance structure. So there's a whole chapter, which we're actually skipping. I think it's chapter 11, all about enolate chemistry, but we're just not doing it in this class. But if you ever see a carbon negative next door to a carbonyl, that negative charge is stabilized. All right, so that is it. Any questions about lecture? All right, let's do some problems. We did a bunch yesterday. We did some synthesis. Reaction yields. Oh, these, yeah, 37. We didn't do 37 yesterday, did we? For some reason, I can't. Last week I did it. I need the. All right, so let's do this one. Let's see what happens. Not the whole thing. I don't think it'll paste it here. Maybe paste it in paint. I don't know why it's. Yeah, it's not doing it. Okay, that's all right. You guys are able to see this. Uh-oh. All right, 43. Sorry, after this, I have a naming question on 1C. I'm unsure how to name a ketone aldehyde together. Yeah, I don't either. That's a good question. So there are several ways. I didn't really talk about it. I mean, I'm not going to have that for you guys, but let's just talk about it anyway, since it is one of the homework problems. Let's see. Oh, it's just saying to propose a structure. I don't think they talk about naming those in this chapter. So it's not something that we're going to have to do. That particular question is just saying, just draw a structure that has a ketone and an aldehyde. But if you did want to do it, basically what you do is you name the aldehyde because the aldehyde has a priority because the carbonyl is on the carbon 1. And then the ketone you name as an oxo, O-X-O. So you tell the reader where it is. So, and I'll go over quickly, but I'm not going to have you guys do that. So like if you have, so the aldehyde gets priority since it's on carbon 1. Let's say I have a ketone there. All right, so here's carbon 1, carbon 2, carbon 3, carbon 4, carbon 1. I start on this side because the aldehyde is carbon 1. So this would be called 3-oxo pentanal. That's basically how you name it. All right, so in this case, the carbonyl is acting as a substituent. The ketone is actually acting as a substituent. Okay, yeah, sure. I did notice that they do actually have one example in the text. That's just why I went over it. Otherwise, I wasn't going to go over it. Where is it at? I saw it right here. Occasionally, the double bond oxygen is considered a substituent, and the prefix oxo is used. I don't think there's any problems that even have that. I think they just show that to you. See, here's a diketone. If it's a diketone, it's a dione. See how right down here they have dione? If it's a dialdehyde, it's a dial. If it's a double bond, I think we talked about enals or enones. But if you have an aldehyde and a ketone, which they aren't the same, yeah, you name the ketone as an oxo. Okay. Okay, so let's, what were we doing? Oh yeah, practice problem. I need to check the 11 already. It was 43, right? Problem 43. Okay, here we go. All right, so let's do all of them. Do all 4 of them. Show you how you'd synthesize all these, starting with cyclohexanone. All right, I'm going to stop the video and go on silent mode. All right. So we can see what I do here. All right, so this is, so we're starting with cyclohexanone. The first one is we're making double bond with the methyl group. Okay. So the first thing you should notice is I am adding a carbon. All right, I'm getting an extra carbon onto my molecule. So we know that if you want to make a carbon-carbon bond or add extra carbons, you do Grignards. So I'm going to do a Grignard on this. So methyl Grignard, MgBr, that's the first step. The second step, now you don't have to show how to make the Grignard. I know that yesterday I went over showing you how to make it. Well, if you just need to use it in the synthesis, you don't have to show me how to make it if it's not asking for that. And then add an acid, and then remember you'll get the methyl group on there, but you will also make an alcohol. So you get the methyl group and you get the alcohol, and then you can, so is there a way to go from an alcohol to a double bond? And yes, that's the dehydration reaction. So adding acid plus heat, we can dehydrate. Remember that mechanism is E1-like. It forms water, and water leaves to give you a carbocation, and you deprotonate it. Okay? So that is that one. Let me erase this. All right, so any questions on that? Next one is the cis-diol. So we have a cis-diol. I'm going to put it over here. Cis-diol. So the best thing to do is to go backwards with these. I didn't go backwards in the last one, but I should have. So go backwards. You have a cis-diol. The way you make cis-diols is chapter 4. You start with a double bond and add KMnO4 with sodium hydroxide. All right, so but now I got to make a double bond. Well, we know several ways to make a double bond. So the book explains the final reaction is H2. Yeah, so remember last week, I think you were here, we talked the difference between a nucleophilic acid and a non-nucleophilic acid. And we said that anytime you see sulfuric acid, that's a non-nucleophilic acid, right? And it's still an acid. It's in water. So remember we said that sulfuric acid and H plus are the same thing. So if you wanted to put H2SO4 in water, that's fine. If you want to just put H plus, that's fine. If you want to put H3O plus, that's fine. If you want to just put the word acid, that's fine. All those mean all the same thing. All right? Okay, yep, no problem. And then, let's see. All right. So in order to get the double bond, so just staying along these lines of the dehydration reaction. Again, H plus and acid. Again, if you wanted to put H2SO4 in water, you can do that too. It's usually heat. I know the book doesn't really talk too much about it, but in class we talked about this. Anytime you want to do an elimination reaction, you usually add heat to it. And then to go from here to this alcohol, you just add, either you can add LAH or you can do the sodium borohydride. Either one of those is fine. Okay. Now, if you wanted to, you could also, we'll do this in a different color just to show that you can go this route. You could have turned this into a halogen, however you want, SOCl2, HBr, whatever. Make it into a halogen, and then just do a regular E2 elimination like we learned in chapter 7 with a big bulky base and heat. So that also works. There's a lot of different ways that you guys can do these at this point because we've learned a lot of ways of how to make the same functional group. All right? Any questions on those two? All right, next one is methyl with a bromine. Methyl with a bromine. All right, so same thing, Grignard. Again, I always put the bromine. I didn't talk about this yesterday. I was going to talk about it yesterday, and time ran out, and I forgot about it. And now, since I just mentioned it, I'm now thinking, oh, I forgot to talk about that. So, the halogen. Remember I said you can either use bromine, chlorine, or iodine. So you can use like methyl chloride, you can use methyl magnesium bromide, methyl magnesium iodide. All right, so if you look on the periodic table, it goes chlorine first, and then bromine, and then iodine on the periodic table. All right, bromine is what's called the Goldilocks halogen. It's called the Goldilocks halogen because it's not too fast, it's not too slow. It's the halogen that's just right. All right, as far as in speed and how things work. All right, usually chlorine reactions go much slower in chlorine, or they don't go at all. Iodine, things usually go really fast, or way too fast, or they're out of control. Bromine is kind of that happy medium that it works well, mostly for everything. So usually what you do is that if you do a reaction where it doesn't matter which halogen you need, you start with bromine. And most of the times, maybe 85% of the time, the reaction works great. You don't have to worry about it. But sometimes, if with bromine, if the reaction goes too fast and you get a lot of side products, you then repeat the reaction, but use chlorine instead, knowing that chlorine is much slower. So if bromine is too fast and wild, you move into a halogen that will slow it down, and it'll work better. If you use bromine and the reaction is too slow and things aren't going as well, then you would go and switch it into the iodide. So a lot of people always ask, like, which halogen should I use? Well, as far as we're concerned, you can use any of them. But then a lot of people say, well, then why would you use the chlorine over the iodine at one time? And sometimes use the bromine. So that's kind of the case. It really all depends on how the halogen affects the overall reaction. But like I said, bromine is kind of that one just right. It works most of the time. But for those times that don't, you have to figure out, should I go to chlorine if it's too slow? I mean, if the bromine is too fast, or if I go to the iodine if the bromine is too slow. So I always put bromine because that's usually what everybody does. But you can do chlorine or iodine. Okay, I don't even remember what the compound is. I think it's a chlorine. Is that correct? It's a bromine. Okay. So then your very last reaction would be to add HBr. Now, technically, that's what your book says. That would be the correct answer. If you put PBr3, I'm okay with that. Your book does say that the PBr3 works better for primaries, and the HBr works better for on tertiaries. And for secondary, you can do either one. But you can put either one. I don't care. Either one is fine. All right. Any questions on that? The next one is that. And then finally, the last one. It's a one-step reaction. It looks complicated, but it's not. So basically what we're doing is we are adding a Grignard. And our Grignard is, let's do line, that's our Grignard. Right there. That whole thing is the Grignard. So you are going to add cyclohexyl Grignard. That green's a little too bright. I won't use that green anymore. And then the second step is adding acid to protonate it. Okay? Any questions? All right. All right, good. Let's see what else there is. Show the products of the reaction with the following reagents. On the product. Oh, yeah, let's do this one. This is a good one. 46. 46. 46 is gone. What we'll do is, rather than taking the break, you know how we always take breaks 10 minutes, how about we just end class like 10 to 15 minutes early? So instead of just, I mean, obviously if you need to go to the bathroom or whatever, you can go. But why don't we just keep going, and then we'll just stop like 10 minutes early or 15 minutes early. All right. All right. Put on pause. So, like I said, do 46. You get practice with those types. All right, guys. Let's go through this. Let's do this. Let's see. That should work. Okay, so draw the products obtained by conjugate addition of the following reagents with cyclohexaene. So cyclohexaene looks like this. Yeah. All right, so the first reaction is with water. So basically, again, how you look at this is a hydrogen. You know, I kind of like to write the nucleophile like this. So this hydrogen will go to this carbon here, and this oxygen will go to that carbon there. So the product will be that. Simple enough. That's basically how you do it for all of them. All right, so for the NH3, your final product will be, basically it's an NH2. So just get rid of the pi bond, get rid of one of the hydrogens on your reagent, and pop the other thing on there. All right, for the alcohol, you're going to make an ether, a keto ether. And then for the sulfur one, you'll have that one. Okay? Makes sense? Any questions on those? I'm going to add one more. Let's do E. So show me what the product is. And this you'll have to do two steps. The first step is here. The second step, remember, in Grignard's is always adding acid. So add this reagent to your cyclohexene. And show me what the product is. So let's do that. That plus ethyl magnesium bromide and acid. I'll give you guys a few minutes to work on that. All right, so in this case, because it's a strong nucleophile, it's not going to go 1,4, it's going to go 1,2. So remember, if you have a strong nucleophile, it goes 1,2 addition. So in this case, your product won't be the conjugate addition, it will be the 1,2 addition. So that will be the product in that case. All right, I just kind of wanted to make sure I gave you an example of when you do the 1,2 versus the 1,4. Remember, the 1,2, strong nucleophiles. And again, you know it's strong because the Grignards have a negative charge. All right, none of these have negative charges. All these are weak nucleophiles, like partial negative charges. All right, So make sure you guys got that. So I gave that one just to make sure that just remember that little rule. You know what? 48 is a good one too, just because there's a lot of different reactions in there. So you see that all right? And make it a little bigger. All right, there we go. 48. So take the structure of carbone. That's the structure of carbone, and then do A through D on it. Do all the reactions. Okay. All right. Put on pause. All right. So we have the carbone. I'm not going to write just space-wise. I'll just write the product. So the first one, LAH. All right. LAH is a reducing agent. It reduces carbonyls and add acid. So it's going to reduce off that carbonyl into, turn it into a alcohol. So your product will be, you still have all of the double bonds. So that would be the product in the case of the LAH. For the Grignard, Grignard's going to go 1,2 addition. That's also a benzyl Grignard. I don't know if you realize that, but that's going to be an aromatic ring. But if you just wrote it as C6H5, that's fine. It's actually an aromatic ring. Again, I told you guys how you know if this is aromatic. If the carbons and hydrogens are roughly the same number or close to it, then you know it's aromatic. That's kind of it. Because a benzene ring is C6H6. So basically, one of the hydrogens is gone on the carbon because the carbon is hooked onto the ring. So if you put an aromatic ring here instead, something like that, that's actually the structure. Next one, hydrogenation. So hydrogenation takes, it hydrogenates your double bonds. Remember, just hydrogen and palladium, it will just hydrogenate all of your carbon-carbon pi bonds. All right, so it should not touch your carbonyl. Now, there are conditions where you can hydrogenate your carbonyl, but I don't believe your book talks about it. So we're just going to assume it hydrogenates out that. And if anyone has the answer book, if you the answer, again, sometimes the answer book does things differently. So I just want to clarify that. All right, because for example, D, there are two possible products that could possibly form. D's kind of one of those where you kind of need more information on exams, quizzes. I would give you more information. So I'd be interested to hear what you see in the answer key. But the two products I would give is either one. I think the one that they want you to do is the 1,4 addition. That's what I'm assuming that they are referring to. So be the 1,4 addition. But these are also the Jacob, I'll submit the. Yeah, thank you. I was going to ask that. I forgot about that. Yeah, if you can give the answers to the chapters. If you can do up to chapter 10, that would be great. So this way we'll have everything. Because chapter 10 is really the last chapter that we'll be doing. 8 to 10, yeah. Because I think 5, 6, and 7 are already posted, correct? Or 4, 6, and 7. I think so. Or 4, 5, was it 4, 5, and 7? 4, 5, and 7. The other possibility is the acetal. So if someone does have the answer key, if you can tell me which product they have, I'd be interested to know what they expect you to do in this case. Because they don't. Because either way, it's the same reagents. I'm guessing it's the 1,4 addition. It's this product here. So if you can tell me, is it compound A or compound B that they give you for the final answer? But if you put either one of these, I'd give you credit for either one. They don't give you a lot of information. It was B. It's the acetal. No kidding. I thought for sure it'd be the A. Okay, so it's B. So it's the acetal. That shouldn't be there. That's interesting. But, okay, so if you put either one, if you put the 1,4 addition or if you put the acetal, I'll give you credit. Even if you put the hemiacetal, because they aren't telling you there's two equivalents. I did think I told you in this book, though, that always assume... Oh, okay, what do you say? Sorry, my internet dropped. Can you explain why you got B? So B is the acetal. B is the acetal compound. So if you take a carbonyl plus an alcohol in the presence of acid, remember it goes through the hemiacetal and the acetal. I told you guys that I would put a number 2 there for the 2 equivalents, but your book does not give you 2 equivalents. They just say 1 equivalent and just expect you to actually know it goes twice. But like I said, either if you put this, I would give you credit based off of how they are asking the question. If I wanted this compound, I would say I would put a 2 there. That obviously is telling me you have to add this twice on the molecule, so you have to think to yourself, what reaction have we learned where you add 2 alcohols onto a carbonyl compound? And the only one we have is the acetal. Okay? All right, good. All right, Hannah. All right, any other questions on those? All right, we have 20, we have 22. Let's do one more. There's a mechanism up here that I kind of like. Let's see. There it is. Question 47. This question right here. How can you explain the observation that the SN2 reaction of dibromomethylbenzene, which is this compound, with sodium hydroxide yields benzaldehyde rather than dihydroxymethylbenzene? So basically, show me a mechanism how you can take hydroxide. Okay, so like water is just a solvent. Ignore the water. Hydroxide. And I'll give you a hint. You need 2 equivalents of this hydroxide. All right, 2 equivalents of the hydroxide. They don't really say it in here, but this question is basically saying you know what an SN2 reaction is, and you know what obviously an aldehyde is. See if you can figure out what the mechanism of this is. Okay. All right, so I'll let you guys work on that for a little bit. Maybe we'll take about 5 minutes. Again, I wanted to end around 1:30, around there, 1:35. So I'll give you about 5 minutes, and you guys work on that mechanism. All right. Okay, let's go over this. Looks like 3 people said they're ready, but let's go over this just for time-wise. So let me go over here. So one of the things I actually find easier, I think I've told you guys this many times, is when you have a compound, write out all the bonds. Don't keep it in the condensed form. Just write it out. And I also told you that you're going to need 2 equivalents of the sodium hydroxide. But it's actually, again, it's only the hydroxide that we care about. Remember, the sodium, you always ignore the sodium. I'm going to erase that too, just because it's in play. And then we know that the final product is an aldehyde. So obviously the bromines are leaving, plus it tells you it's SN2. So you know the hydroxide has to add in there and kick out one of the bromines. Okay? So obviously this oxygen is going to be on the carbon, and this hydrogen will stay. Okay, but both bromines are leaving. Okay, and it tells you it's got to be an SN2. All right, so the first step is that the hydroxide adds and kicks out a bromine. As they tell you, I'm going to put pH for the shorthand for the aromatic ring. So one of your bromines leave, you'll have the OH here, plus you'll have the hydrogen, plus you'll have another bromine. All right, so all we did is we substituted the OH for a bromine. Okay, and you should be thinking to yourself, all right, I have to get a pi bond, so I have to take off this hydrogen. Obviously, that hydrogen has to be removed. This bromine has to leave, and I need a pi bond over here. Okay, so if you have another equivalent hydroxide, so you have another equivalent of hydroxide, which is a base. What can happen is this is going to pluck off this hydrogen. These are going to pop down to form your pi bond, because that's how you form pi bonds, is from these electrons. And we know that bromine is a good leaving group, so your bromine is going to leave, and that will give you that compound. So it's kind of like an elimination reaction. So we've learned elimination reactions look like this. You have a hydrogen here and a halogen here. All right, and you have a base of some sort. Grab the hydrogen, pops down, kicks out the bromine. That's kind of what we have here, except we have a hydrogen attached to an oxygen, attached to a carbon, attached to a bromine. So everything is the same except we have an oxygen here. And you have your base, in this case a hydroxide. It's plucking up the hydrogen, forming the pi bond, and then kicking out your bromine. So it's just a two-step mechanism. A lot of people try to do this. They try to have a carbon with two hydroxides on it. Two H's. What they'll have is, and then they'll have the hydroxide again add into there and replace a bromine. All right, if you notice, that's a hydrated carbonyl. Remember from the hemiacetal, acetal, if you take a carbonyl and you add water to it, you get the dihydrate. So if you went that way, you would need acid in order to break this down. But we aren't in an acidic environment. We're in a hydroxide environment. So in this case, you're doing kind of like an E2 elimination. This is E2 like how I talked about over here. Okay? So just kind of a different type of mechanism, just to kind of take what we've learned so far and see if you can apply it and see that even though this isn't the classic E2 elimination or SN2 or an oxidation, how we normally form aldehydes, it takes what we've learned and kind of shows you how the knowledge you've learned so far, you can pretty much do any type of reaction. And even though we haven't seen it before, we can kind of try to figure it out based off of stuff that we've learned so far. All right. Okay. Well, that's all I have for today. If there's any other questions, I'm more than happy to answer them. Otherwise, I will see you guys tomorrow, Thursday, for the problem review. So if you have a question, just kind of go unmute or something.
I have a question, actually.
Sure.
It's kind of on the topic. Just in general, do you have any advice? Because I know everyone's kind of got a lot of stuff going on with world events and like with work. Like, what's your advice for, like, if I feel like we